So, you can weigh a galaxy. By the way, we're on page 432. This is chapter 16. You can weigh a galaxy by seeing how fast it spins. The more mass it has, the faster the spin will be. And you can tell spin by the Doppler effect. You can shoot, you can look at the light coming from this area, and if it's coming towards you, it's said to be what shifted? Y'all remember? Blue shifted means it's coming towards you. And so this side coming towards you, and you can tell how fast by how far it's blue shifted. This side going away from you, you can tell how fast by how far it's red shifted. And that'll give you an idea of the weight of the galaxy. These are some graphs showing the rotational speed. Galaxies, the different parts of a galaxy don't rotate the same. The closer you are to the center, the faster you'll rotate. And the further you are from the center, the slower you rotate. So they have what's called differential rotation. Stuff near the center is going around fast. And stuff further out is going around slower. It's just like the planets in our solar system. Mercury goes around once in how many days? Do you know?
58.
88 days. Good guess.
Oh, dear God.
Earth goes around once in 365 days.
Really?
And Saturn just goes around once every 22 years or so.
That's close.
30 years, something like that. Might be even more than that. I don't know. Anyway, so these galaxies have differential rotation, but you can still tell how much the galaxy weighs by how fast it's spinning. You can also tell how much galaxies weigh by how fast they move around one another. These two galaxies are orbiting one another. They're kind of going around in space like this. And so you could tell if a galaxy was heavier, it would be pulling its neighbor faster. You see? If it's lighter, it wouldn't be pulling its neighbor as fast. And so you can look at the red shift and blue shift of galaxies as they move around one another to get a determination of their mass. And often galaxies are in clusters, and they're all moving around one another. And so you can input this into computers, and a computer can simulate the movement of all these galaxies. You just have to enter the location of the galaxy and the red shift or blue shift that you're getting to determine the movement. It'll be neither red shifted or blue shifted if it's moving perpendicular to the observer. See, this one's moving away, so it's red shifted. This one's moving toward the observer, so it's blue shifted. And this one's moving perpendicular to the observer, so you're not getting a red shift or a blue shift. So you input all this into a computer, the brightness of the galaxy, the movement of the galaxy, and the computer can do a simulation of these and tell you how much the different galaxies weigh. Computers can do lots of mathematical calculations very quickly. So they're useful. And so, like I said, I touched on in the last chapter, we know from all these masses that all galaxies weigh a lot more than you'd expect them to. If you look at the light matter in a galaxy, this galaxy might have a mass, if it's like our Milky Way, it might have a mass of 500 billion suns. That means it might have about 400 billion stars and then a bunch of other gas and dust floating around that maybe gives it another 20% mass. So 500, our galaxy might weigh about 500 billion times what the sun weighs. Or something like that. And you can get an idea of how many stars it has and such. And that'll give you an idea of the visible. Give you if you mass the galaxy, you can get an idea of how many stars it has. You can also get an idea of how many stars it has by its brightness. You know, the more stars it has, the brighter it will be, right? And we find out that the mass that galaxies have is way more than the brightness that they have. And we find out the speed that they're spinning is more than we'd expect, based on the brightness of the galaxy. In other words, there's a lot of mass in galaxies that's unaccounted for. And this picture is showing that as this blue haze. The blue haze is what we call dark matter. And the light area, that's what we call light matter. Light matter is matter that you can see. And dark matter is matter you can't see. And we figure that every galaxy is surrounded by a huge, what we call a dark matter halo. There's a whole bunch of dark matter here, with the little light matter in the middle. We can see this. We can't see this. But we know this is there because of its gravity. We don't know what it is. Scientists think that it's probably some elementary particle that we haven't been able to discover yet. And it's not that it's outside the galaxy, it's in it too. This dark matter is pervasive all throughout the galaxy. And when you look for the weight of these galaxies, we find out that only maybe 10% of the mass, or it might even be less, 5% of the mass is dark matter. And maybe 90 to 95%, 5% of the mass is light matter. And 90 to 95% of the mass is dark matter. So this dark matter, there's a lot of it. Scientists estimate if it is some elementary particle that we haven't discovered yet, that there's probably trillions of them going through your body right now. The dark matter has very little mass, but it has some mass. And it's a real teeny particle with probably no charge. Kind of like a neutron in an atom. Y'all remember you learned about protons and neutrons and electrons? These are elementary particles. There's probably some other elementary particle out there that we don't know about. It's dark matter. It doesn't shine any light, and it's got very little mass, and it doesn't react much with any of the other particles. It kind of just goes right through them. So this stuff could be all around us, but so small we can't see it. So uncharged, it doesn't react with anything, and it goes right through us, and the only thing it has is a little bit of mass, but when you add up all of its mass, you get something real heavy. Did you have a question?
No.
No? Okay.
That camera out of my face.
Okay.
It seems that every galaxy has this dark matter halo. And there are some galaxies out there that have no light matter, only dark matter. Because you'll see a galaxy orbiting another one. But one of the galaxies you can't see. There's nothing there. But this one's orbiting it. So we know it's there, but it must all be dark matter. Isn't that freaking crazy? Have you ever been flying in a plane and you look down and you see the waves? You can't really see the waves themselves, but you can see them crest every once in a while. And you see little white foam on top, and you know that that's a wave. You know there's a big wave underneath it, but you can only see the cresting white foam. Have you ever experienced this when you're flying in your private jets and such? I have when I'm flying in my private jet. It's a G7. I've got that kind of cash. Anyway, you look down, and way down there, there's this little crest. The crest is like the light matter, and you know there's a giant wave below it, and that's the dark matter. That's a good way of thinking about it. I like that. Here's another look at it. There's a galaxy. All this is luminous matter that we can see. And those, you know what those red dots represent?
Globular clusters.
Very nice, globular clusters. And then all of this is dark matter.
If someone went behind the dark matter, you could still see them?
Yes, you can still see stuff behind the dark matter. The only thing that clues us in that the dark matter is even there is its gravity. Because its gravity is strong and definite. And you only see it its gravity on large scales. If you're looking on the scale of galaxies, you'll experience its gravity. If you're looking on the scale of just looking at a star, you can't sense its gravity because it's everywhere, you see, and it's all throughout. Sorry,
Dark matter, you can see through it.
You can see right through it. It doesn't give off any light, and it doesn't affect light. It's transparent, but its gravity can affect the light. Do y'all remember? Einstein showed us that gravity can bend light.
Yeah.
Remember the instance of the eclipse, and the stars appeared to move a little bit when you could see when the light's coming near the sun that the sun bends the light. It's the same thing with this dark matter halo. That will bend light, and you can tell it's there by the bending of the light. That's called gravitational lensing. It's really cool. I'll show you gravitational lensing in just a second. Dark matter is important. It's probably the biggest discovery of my lifetime.
This is a two-part animation that addresses dark matter. Observations of hot X-ray producing gas in galaxy clusters, shown in red, provide a measure of the amount of dark matter present, shown in purple. These observations can also help determine the composition of the mysterious dark matter. In this first part, substellar objects are collapsed stars. In the second part of the animation, we show the galaxy luster again, but in this case, an alternate form of dark matter is cartooned, mainly as exotic elementary particles left over from the Big Bang.
I'm not exactly sure what that video was saying. Let's get this. Galaxies. So the first section is about dark matter. The second section is about galaxy collisions. Oh, one thing he did say in that video, we think the dark matter may have when the universe was real small. Remember, the Big Bang was an expansion of the universe. From a very small point, the universe expanded and got as big as it did today. And imagine if you rewound that and went backwards. When the universe is really small, it'd be incredibly hot. Imagine taking all the stars and all the galaxies and cramming them in a very small space. At one point, the universe was as big as as big as this mouse. Imagine every star in the entire universe, all that energy, crammed into that little bit of space. You think it'd be hot? It'd be unbelievably hot. It'd be almost incalculably hot.
Very heavy.
And scientists think that and very heavy, you're right. Scientists think that at energy is so high that maybe these dark matter particles are created. So when the universe expands, when they say these particles were left over from the Big Bang, what they're talking about is at the high energies that the Big Bang produced at the very beginning, it may have been able to, at those energies, produce these particles. So to test if any of this stuff is true, what they do is they take these big particle accelerators. Have you ever heard of those? They just built one in Europe called the Large Hadron Collider. You ever heard of that?
It's an angels and demons.
The LHC, yeah, it's a big ring, and it's huge. It's like 20 miles in diameter, and they get particles like protons, and they put them in there, and they start speeding them up using magnets, and they can get them going real fast around in circles. And they can get these protons going at 0.9999 times the speed of light. I mean, they're just going around. They're going around that thing maybe 1,000 times in a second. More than that. 10,000 times in 1 second around this 20-mile circle of track. And then they get another one going in the opposite direction, you see? And they get them going, and they get them going, and then they make it, they move the magnet so they collide. Bam! And at those energies, it's so hot where they collide that it starts to approach temperatures in the Big Bang. It starts to approach these huge temperatures that you don't even get. I mean, it's hotter there than it is even inside stars. And these protons will collide and blow up, and maybe, just maybe, they'll produce some dark matter. Or some other fundamental particles we don't know about. That's what they're doing in these large collider experiments. If you hear about this thing, the Large Hadron Collider, like 8 countries went in on it. It's so expensive that one country couldn't afford it. So many countries go in on it together. America was one of the countries. And they built this thing. It was like $10 billion machine. And so they're trying to maybe create some dark matter or some other types of things that they're not haven't understood. This is showing galaxy collisions. Galaxy collisions are beautiful. They happen so slowly, though. We can get pictures like those are 2 colliding galaxies, but they aren't going to collide and move through one another in our lifetime. It takes billions of years for them to actually move through one another, or hundreds of millions of years at least. And so what we think is that galaxy collisions formed the galaxies like we have them today. You can imagine when the universe was much smaller. Remember, the universe has been expanding. So if you rewind that and you go to a point where it was smaller, but when the universe was smaller, galaxy collisions were more frequent. There's a lot more traffic around. And if you're a galaxy, you're much more likely to run into another galaxy if the universe is small. With the universe as big as it is now, galaxies don't collide that often. Are you with me, Olivia? It's amazing stuff. But when the universe was small, galaxies collided more. So where would you see colliding galaxies if you're looking at a telescope?
The edge of the... Never mind, I'm kidding.
No, you're right.
Okay, never mind.
Say it again.
The edge of the universe?
That's right. You would see them very, very far away. Because when you look far away, you're looking backwards in time to a time when the universe was smaller. And then you'd see more collisions, which is exactly what they see. So at one point, there were a lot of galaxies all crammed together, and they would collide. And when galaxies collide, they eventually come together and form a larger galaxy. And these galaxy collisions keep taking place. And sooner or later, you go from a lot of small galaxies to a few larger galaxies, which is what we have today. That's a visible picture from a long time ago, looking at the galaxies when they were smaller. This is called the Hubble Deep Field. They took the Hubble Space Telescope and they pointed it at one area and left the shutter open and left it pointing at one area for something like a week. And it kept taking in light and brightening the picture and brightening the picture. This is what they got. They did it twice. They did it looking north and looking south. North, like of the North Pole, and south of the South Pole. And this was a completely dark area of the sky. They chose the darkest area of the sky that they could find. And they said, there, let's focus on that point. There's nothing there. And let's focus in as far as we can for as long as we can. So just a tiny portion of the sky. a little tiny, less than 1 degree of the sky, less than 1 second of the sky. And this is the picture they got after exposing it for 2 weeks. Every dot you see is a galaxy. Perhaps some of them as big as ours, but most of them smaller, since it's looking a long time ago when galaxies were small. These numbers show the distance to the galaxies. I think. Numerous small, irregularly shaped young galaxies can be seen in this very deep optical image, known as the Hubble Deep Field North. This image, made with an exposure of approximately 100 hours, so that's about 4 or 5 days, captured objects as faint as 30th magnitude. Redshift measurements, as denoted by the superimposed values observed at the Keck Observatory in Hawaii, indicate that some of these galaxies lie well over 1,000 megaparsecs from Earth. The field of view is 2 arc-minutes across, less than 1% the area subtended by the full moon. 2 arc-minutes, not arc-seconds. That's a very small area of the sky, and look at all this. And so what you do is you input this image into a computer. The computer counts the number of galaxies, and then it does it south, and it does the same thing. It counts the number of galaxies, and it averages the 2 numbers. And then you just multiply by how many of these little areas it would take to completely cover the sky, and you have a count of how many galaxies there are or were at one time in the universe. And that number comes to somewhere around a couple hundred billion. There's a couple hundred billion other galaxies out there. Of course, this was a long time ago, and some of them have merged to form bigger galaxies. A lot of them have merged to form bigger galaxies. But this is the best picture that we have of the edge of the visible universe. We're going to get a better picture when they launch the new satellite that's going to replace the Hubble. And that'll come up in about 5 years. It's about 10 times as powerful as the Hubble. I forget the name of it. The James Webb Space Telescope. Look for that in 5 or 6 years.
This sequence of still images demonstrates that a small, relatively empty-looking portion of the sky is actually filled with thousands of galaxies when viewed at the famous limits of the current-day telescopes, about 30th magnitude. This faint threshold reveals...
So they did that real quick. Check this out. Have y'all ever seen the Big Dipper?
Mm-hmm.
Here's where the Hubble Deep Field focused, right there. So we're zooming in on that portion of the sky.
This faint threshold reveals objects that are less than 1/1000th the brightness of the faintest stars as seen by the human eye. The final image in this sequence was taken by the Hubble Space Telescope, which focused on a small region near the Big Dipper for more than 100 hours of exposure time.
Isn't that cool? That's zooming way in. The book goes on and talks about these galaxy interactions. Galactic cannibalism. That's a great term. That's when one galaxy absorbs another one. It talks about how a big galaxy can rip apart a smaller galaxy because of its gravity. And I got some good video footage of galaxy collisions here. You have to understand, when 2 galaxies collide, even though they're made of billions of stars, almost none of the stars collide. Because the stars are so small compared to all the space around them. Even though a galaxy looks so bright and big, it's mostly empty space. The stars are just tiny little specks. And so when two galaxies hit each other, the stars go right past each other. They almost never collide. But the gravity changes the shape of the galaxy. The gravity of the interaction changes the shape. And so here we go. Here's two elliptical galaxies come along, and it changes the shape of an elliptical galaxy to a spiral galaxy. This is a computer simulation. Watch the two. Two elliptical galaxies. The gravity changed the shape of them, you see. And now you got spiral galaxies. So it's thought that most spiral galaxies like ours were probably once elliptical galaxies. Now these two, they're going to end up coming together to form one single galaxy.
Wait, did they just shoot off stars on top of right?
Yeah, these are all stars and gas go shooting off.
That's not nice.
But they'll fall back in eventually. And this is done with supercomputers that you used to not even be able to do these simulations. It takes the largest computers in the world to run these simulations because there's so much math. You got to calculate the position of every star, and there's 400 billion stars. There, it's run real quick. The actual simulation might have taken a week to run. And then they just fast forward it after that. Galaxy Collision 2.
This computer-generated simulation shows the collision of two spiral galaxies. Tidal forces in galactic rotation cause the galaxies to cast off stars and gas in the form of long, thin tidal tails, similar to those observed in the collision of real galaxy pairs. As the galaxies pass by one another, their disks become distorted, forming prominent bars and spiral features. The mutual gravitational attraction of galaxies swings them around and causes them to fall back and merge into a single object. These so-called numerical experiments allow astronomers to study the dynamic interactions of huge galaxies over millions of years of simulated time. Such environmental changes are among many ways that galaxies can change shape.
And when that would happen, the two black holes that are at the center of each galaxy would eventually merge together and form an even bigger black hole.
Can I go to the restroom, Mr. Willis?
Yeah. So we get this final view toward the end of this chapter. They show that smaller galaxies can come together, merge into larger galaxies, and these mergers continue, forming spiral galaxies or large elliptical galaxies. Basically, the idea of this is it's showing galaxy evolution. Small galaxies make larger galaxies. At some point, they become active when the black hole in the middle is feeding. And this shows an active radio galaxy with these large radio lobes. And this is called a Seyfert galaxy. But anyway, the modern galaxies of today were formed by mergers between smaller galaxies. Mergers and interactions are real big. And so when we take all these pictures with our telescopes, we can map out our universe. And this is showing a map of the universe. Again, we've already seen this picture. The Milky Way will be at the very center. There's a huge galaxy cluster near us called Virgo. There's one down here called Hydra. If we show it in 3D, here's where we are. And here's the Virgo cluster of galaxies. There's another cluster of galaxies over here called Perseus. That's kind of how it looks 3D. The Coma cluster is up here. This shape is the shape of these large galaxy clusters. It might consist of millions of galaxies kind of huddled together. And this is huge swaths of deep space where there's not much stuff. The clusters can move around and hit one another and merge to form larger clusters.
This dramatic animation shows the close encounter and eventual merger of two colossal groups of galaxies. Although no dramatic fireworks result, loose gas in the galaxy's clusters collide with speeds greater than 400 kilometers per second, or 1,000,000 miles per hour. As the clusters merge, the gas is heated to 100 million Kelvin. Such superhot gas, shown here glowing in red, can be detected only with X-ray telescopes in orbit.
Queen Kathleen, you're missing all this. Your Majesty. We find when we map all these galaxies, we find further structure. We find that there are bubbles. The galaxies are arranged in lines. That they call this line of galaxies that they've circled here, they call this the Great Wall, where the galaxies are almost lined up. And then there are big spaces called voids. And this line of galaxies is three-dimensional. It actually comes out at you. So going around, if you continue this all the way around, there's a big circle, a line. This Great Wall continues and comes out at you like this. It's like there's a huge bubble of galaxies in space forming a line. They don't think this is by accident. They think there are forces so strong when the Big Bang was happening and the universe was expanding that kind of dragged a bunch of material together that formed galaxies all in a line. You know, if you kind of move your hand through the water, you'll form kind of a wave that moves along. And even behind your hand, as you move your hand forward, there'll be kind of a wake. You know what I'm saying? The wake is kind of the void, you see, and the hand moving is compressing the water together to make the wave. So we have like waves of galaxies, waves of material that forms into galaxies, and then voids behind it. These are the largest structures that we know of in the universe. These great walls and voids. And they think it's from the Big Bang when the universe expanded. Like beads on a string, galaxies kind of in a line, with spaces in front of it or behind it. This is even going farther back. Every dot is a galaxy. That line shows the Great Wall. Here's another. You see that line? See there's kind of a bubble-looking thing there? Beyond that, we don't see any larger structures. This is looking north. This is all the galaxies looking north, and this is all the galaxies looking south. This is what scientists are doing right now with their huge telescopes. They're charting the universe. And these are only thin slivers of space looking north and south. Remember, this goes out in every direction. In the brain of a computer somewhere, there's a 3D map of the universe showing all the galaxies we've ever seen. Can you imagine how much data that is?
A lot.
Absolutely.
2 grams.
So we're at the middle there. They're not only charting the light matter, they're charting the dark matter too. Where is the dark matter? Remember I said there are some galaxies out there that are just dark matter, a bunch of dark matter in one area and no light matter? They can tell that by what they call quasar mirages. And that's what they're showing here. You see how that and that, those two things, that looks like separate galaxies? They're not. Those are the same galaxy. They've been lensed. Gravitational lensing has occurred. Let me show you how that works. Here's a far-off quasar, which is an active galaxy that's emitting a lot of light. The light from that quasar goes around an object, another galaxy, and is lensed and comes back to the eye of the observer, and the observer will see two separate images, but it's actually a single image. Only the light from that image has been lensed around the intervening galaxy. If this intervening galaxy is dark matter, you won't see anything in the middle, but you'll see two identical images. And you know that there's something in the middle. This is called Einstein's cross. 1, 2, 3, 4. Those 4 blips there are all the same thing. It's a single object. There's a galaxy in the middle, and that galaxy has lensed those 4 objects so that we see the light. The light of one object that's behind this thing, we see it in 4 different places. If everything works out just right, you'll see a sphere of light. If the shape of the object is just right, it's almost like a lens moving in front of a light. If I have a lens moving through space, and it goes in front of a flashlight, you'll see a circle of light as the lens moves in front of the flashlight. I need a flashlight. You'll see a nice circle. And you can't see the lens. Of course, you can see it here because I'm holding it. But if it's dark matter, you wouldn't be able to see it at all. But you see the bending of the light. Gravitational lensing is what that's called. This is an important tool. Look at this picture. Do you see those streaks there? Those are lensed, that's lensed light, forming kind of a circle. I want to go back because I noticed it in the very first picture of this PowerPoint. This is just really cool stuff to me. Been through a lot of slides here. Do you notice lensing going on here? You see how that's kind of streaked out? And over here on the side, I guess it's not as noticeable as I thought it was. That one's kind of streaked out a little bit too. Not as noticeable there. Never mind. Sorry. But in this picture, you can see it real well. The light from these stars is all streaked, and that's because of lensing. It's like a lens has moved in front of those stars, and the light from stars back here is spread out and is lensed and is coming back at us. And so we know that there's intervening mass between us and the picture taken. And you can enter this picture in a computer, and the computer will figure out, based on those streaks, where the object is back here. And how much mass is in front of it. You can see here some streaks. See that? That's a streak right there. And there's streaks over here on this side. And it means there's some kind of matter in between us and the objects behind it, distorting it. And that's dark matter. And so here is a picture taken with a regular telescope. That's visible light. And here the computer has made a map of the dark matter in the area. So you read chapter 16. We'll finish our lab tomorrow with the stars.